Okay, so welcome to the final session of MFPS, or one of the two final sessions of MFPS. So I'm not sure, I mean, I've been 40 years in MFPS. I don't know if it's ever had a parallel session before. And it's not something particularly that we wanted to aim for, but in the end, turned out to be the what seemed like the only solution to a scheduling problem. So anyway, thank you for coming to this session. The first speaker is Alex Kavvos, University of Bristol. Hopefully we've all seen part one. This is two-dimensional Kripke Semantics part two.
Thank you very much, Alex. This is indeed one of those talks where you haven't seen part one, but it's not you will see why it's slightly better than the first. There's also something very special about the fact that Alex Simpson is chairing the session. He chaired my very first talk in Uppsala, Concepts 2017. I was very nervous. I go up there, I give my presentation, and then he gives me a cheeky look and pulls out his thesis proposal from the year I was born. Half my thesis is in there. Some more stuff that's also in this talk was also in there. I hope it's not the whole thing. Let's just go. So, two-dimensional Kripke semantics. What's all this about? Modal logic is an important logic in computer science. It has some intentional flavors. It can tell you all sorts of interesting things. It's temporal, epistemic, dynamic logic, Henderson modal logic, concurrency, and so on. Now, all this stuff, both philosophers and computer scientists like to see with Kripke semantics. Some kind of world thing with some relation between worlds or some concept. Very easy to think about, very easy to reason about, even for undergraduates. But in type theory, which is something we do in programming languages, proofs are important. The Curry-Howard-Lambert correspondence and all this stuff. And type theoretic modalities arise everywhere. And all of them are interesting and important. They can capture things such as logical time. For example, Lars Berkedal with his synthetic guarded domain theory has done a lot of this stuff. Proof relevance, Frank Fenning in the early 2000s. Globality, that's important in Martin Hofmann's high-order abstract syntax models. Information flow of more recent years. Thing is, column A and column B don't connect at all. This project is about connecting the two and drawing a very long line, connecting stuff that happened from the 40s onwards, maybe the late 50s, till today. This talk, this paper could have been done 40 years ago. Why it wasn't is an open question. Okay, brief intro to semantics of intuitionistic logic, the simplest place where you need Kripke semantics. There's two kinds. There's spatial semantics and algebraic semantics, and they are in some kind of duality that I'll talk about in a moment. The basic thing you have here is a Kripke semantics. You've got some worlds, you have a poset that denotes information increase. Bottom is never true. An implication is true if in any future world where more information is gleaned, if the antecedent becomes true, so does the consequent. And this is famously monotonic. That's the most specific semantics of intuitionistic logic. It sounded complete. The most general semantics, as long as you don't like proofs, are Heyting algebras, which are exactly take the rules of intuitionistic logic, make them into an algebra, talk about this or right. I'll show you a construction that goes from A to B. This project is also about categorifying, so going one step further to reveal proofs. We've known this for quite some time now. Also, this is dedicated to Bill Scott. This session that we had on Wednesday, we've known that semantics is Cartesian or either bi-Cartesian closed categories, if you also want this structure. The question is what to put here. And I'll show you that there's a very simple generalization of this stuff, where if you replace the poset by a category, and you think of the category as a proof-relevant poset. So the objects are the worlds, the morphisms are increases in information, which are evidenced. Transitivities, composition, and so on and so forth. There's a very simple semantics that actually coincides with the pre-shift interpretation of intuitionistic logic. So in any pre-shift category. Right, all this is known. If you want to do modal logic, and in particular intuitionistic modal logic, which you want to do type theory, then you've got to fill out the same table for intuitionistic modal logic. And oh my God, where to start? Okay, all of these things, there are various different ways of filling these boxes, but the one that we know in the last at least 5-6 years absolutely works is this one. So the algebraic semantics with proofs should be a bi-Cartesian closed category with an adjunction. That's something that Bill Lorvier would call an objective answer to what a modal logic is, at least categorically. You don't have to think about the proof theory, about how lambda calculi and things like that. You can just work with the thing in abstract up to categorical equivalence and you should be fine. Okay, that was proposed by Clausen, and Clausen did some excellent work on showing that this comes from Fitch-style natural deduction. If you've been trained as a computer scientist, you've read Huth and Ryan's book. And in that book, the first thing you learn is Fitch-style. It's easy to decategorify that. So if you want to kill proofs, what you have? You've got a Heyting algebra with a Galois connection. Top of it. Okay, that's easy. It turns out that kind of thing, if it's a particular kind of Heyting algebra, comes from a Kripke semantics equipped with a bi-module. I'll talk about that later. And if you want to reintroduce proofs, what you can do is you can take a cat ring and you can have a profunctor. You see, a profunctor has a proof-relevant relation which replaces the bi-module, which is a relation that's compatible with a poset. This is a proof-relevant relation compatible with a cat ring. Okay, so this is what this program is about. Since you haven't seen part one, I'll summarize very briefly what happened in part one and then tell you about part two. Any questions so far about where I'm going? Okay, right. So there's a very simple construction that takes us from Kripke semantics to Heyting algebras. And it's the following. Kripke semantics happens in a Kripke frame, which is a partial order. Take the partial order consisting of 0 and 1 with 0 less than 1, and then take monotone functions out of this partial order. If you squint, you'll realize that's just the upper sets of W. So they are the sets where if you have a world in the set, any world that contains more information is also in there. This thing is a complete Heyting algebra. It has arbitrary joins and meets. It's a very easy way to get a complete Heyting algebra out of any partial order. It has a beautiful thing, the principal upper set embedding. So this is a monotone map from the op of W into this that embeds every world as the set, the upper set of worlds that contain more information. If you squint, that's the Yoneda embedding, but we're not seeing that yet. This preserves meets and exponentials, but be careful, the meets are being opt here, so they are actually joins. The question is, when you embed W into these upper sets, how do you recognize the things that come from the embedding? And you can actually see them because they are of that form, so they are in the image of this map, if and only if they are prime. And prime things are very interesting. I didn't know about primes before starting this project. I think they're wonderful. Look at that. So suppose you've got some kind of big least upper bound. Remember, we are in a complete setting. We have arbitrary upper bounds. An element is prime. Whenever it is less than something that's a least upper bound, it's less than something in that least upper bound. So to be prime is to be an indivisible unit of information, is to have the least information possible that something is just over a world. Moreover, every upper set, so everything in this lovely poset can be reconstructed as a join of primes. So you take a big join of all the upper sets, essentially you can draw this. May I use the board? Is it visible? If you think of an upper set, something that's upper closed, other color. What you can do is you can, never mind. It's too much time. Look at everything. Okay. So if you've got an upper set, that's something that's up directed, you can take every point, everything that's bigger than that, and if you union them all together, you can reconstruct the entire upper set. So everything can be reconstructed as a union, that form. Such things are known as prime algebraic lattices. They've been very important in Glyn Winston's work for a very long time. They come from the 80s and the 50s, and there's a theorem that says that there's duality. If you take posets and monotone maps, you flip that category over, you get prime algebraic lattices. So every prime algebraic lattice is of this form. It's the upper sets of some kind of world thing. And that's how you see within Heyting algebras, that's how you obtain Kripke semantics. This, by the way, can be refined. I'm not going to talk much about this, but if you take functional simulations here, so not bisimulations, only one-sided simulations that are functional, over here, the corresponding maps are things that preserve exponentials. So something that preserves truth over here corresponds to something that preserves inference on the other side. Isn't that interesting? Okay, all that has been known since 1981. Never seen it before, written down. Okay, now add proofs. Really very simple. I'm not going to bother non-capital theorists with this. This is the logic session after all. But you just replace 2 by set. Set is a situation where you have one proof of false, the empty set, no proofs, and every true proposition is interpreted by a set of possible proofs. Okay, and replace the arbitrary Kripke frame by a category, and then take free sheaves. If I flip very fast between those two slides, you can see that there's a completely similar story. It's a co-complete Cartesian closed category. You've got the Unade embedding, it preserves products and exponentials. A pre-sheaf, remember before you had an element that was prime, a pre-sheaf is tiny. If you take this HOM thing, so if you take all the maps from this pre-sheaf elsewhere, you take this, and that's a pre-sheaf itself, if that thing preserves co-limits. Moreover, you get to see new structure that you couldn't see in the lattice theory case. So here we have an if and only if. Now you've got to be careful. C must be quasi complete for this to be an if and only if. So to regain C from the category of free sheaves, C must have been nice, or you can canonically get a quasi complete thing. Every free sheaf is a co-limit of tiny objects. So if you take a bunch of Unade things, you stick them together in a particular shape, you can get P back. Perfectly the same thing. The duality, of course, generalizes. There's a theorem by Martha Bunch from a thesis. It says if you take quasi complete categories and you opt that, you get essentially what's pre-sheaf categories, which can be categorized as having all this stuff. So what is a two-dimensional Kripke semantics? Only took me 10 minutes. It's a semantics in this category, the category of pre-sheafs. Okay, that has been known for 30 years, maybe the early 80s. And it didn't have right. Okay, there's no modal stuff here. How do I add a modality? That's been a big question that's been answered in many, many different ways, but I've shown there seems to be a canonical way. So this requires a little bit of Khan extension, so don't be scared if you haven't seen this before. So I told you can embed any such W in in this prime algebraic lattice, and that thing on top there is an embedding. That's an order embedding. If you've got any other complete thing and a function to it, you can extend this to the entire prime algebraic lattice. Why? Because this thing is made up of prime things. So you decompose into little primes, you ask F, what would you do on that prime thing? And then you do the same thing. Here's the definition. You can follow that. This is Johnston's book, Stone Spaces. That has a right adjoint for free. You can read that, you don't have to, but you could. Okay, so how do I get modalities from this? To have modal logic, you need some kind of relation. You need to be able to say how to go from one world to another. One way is to increase in information. But you can also have an extra relation, something else that is compatible with increase in information. And the canonical thing to do, which you've seen in our category theory, is to use a bimodal. So if you've got W related to V, and you can decrease information on the left or increase information on the right, the relation should be closed under that. The name, of course, comes from algebra, and in particular, homological algebra. Okay, equivalently, what can I do with this? I can see it as a function into truth values, 0 or 1, from W op times W. So it's op from the first component, so that information can reduce on the left, increase on the right, and that needs to be monotone. Here's the trick. Lambda abstract the second component, move it over here. You get a monotone function into the prime algebraic lattice from W op, here it is. Here's your embedding. Take the Khan extension. Ooh, I said a bad word. Take the extension. If you look at what this does, if you calculate this map, if S is a predicate, it's true in some worlds, it's an upper set in particular. Black diamond of S is true in all worlds, such that there exists a previous world where S was true. It's the modality you know, it's your diamond, but it's black because it's in the opposite direction. It's a Jekyll and Hyde thing. This is Hyde. If you look at the right adjoint of this, by the way, this map by itself, extremely well known by model logicians. The fact it's a Khan extension, I've never seen it before. It has a right adjoint. If someone has, please tell me, I need to cite it. The first paper on this has 106 citations, it needs some more. The right one, which is the adjoint to this, automatically given, is the usual box operator. And in particular, by precomposing the left adjoint with this, you always get a correspondence. So you get that every such bimodule corresponds to an adjunction like this. And you can make this into a categorical duality. Okay, if you lift this to categories, If you replace by module with a category and then a pro filter, of course you complete category, please. Use the left card extension, that becomes your nadir, that's the left card extension. It has a right adjoint automatically. If you write down what these are, so this is an upper set, it's a pre-sheaf. At world W, this is a coend. If you don't know what a coend is, don't worry. It means something in there and these two things, but these two things, they are like communicating glasses. So something can move from one side to the other in a contravariant and covariant way. So it's a V, a proof that we can go from V to W, which was our current world, and a proof that P is true at V. And vice versa, and I thank Matteo Capucci for this, put it on Twitter. You get the very same thing for the box, which is just natural transformations, because this one is an end. So it's for all V's that I have a proof I can go to from this current world, P is true there. So with two-dimensional Kripke semantics, uniquely is an adjunction on pre-sheaves. Okay, that was the first paper. I've got 15 minutes, less than that for the second paper. Excuse me. Okay, so every Kripke semantics induces a prime algebraic methods. How do I go back? If you read any classic text and modal logic, you will find that there is a construction for going back that takes a fighting algebra and produces Kripke semantics. And the way it does that is it takes prime filters. And that is how you prove completeness in any traditional book. However, the stuff we've done now proves relative completeness already. So if a formula is true in all fighting algebras, it's true in all prime algebraic lattices, therefore it's true in all Kripke semantics. So if the Kripke semantics is complete, it's provable. So the algebraic semantics is as complete as Kripke. The opposite direction, you get a Kripke frame of prime filters. The earliest place I found this is the book by Melvin Fitting. If you know of an earlier reference, please let me know. And you can show the same kind of thing. For this logic that this induces, which is the logic of Galois connections, it's been done by Zick, Yarvinen, and Kondo. But it's highly non-constructive because taking prime filters, if you don't know what these are, is a weak form of choice. It's not exactly a choice, but it's not constructive either. So we can't really make it into category theory. So I asked myself, how do I proceed with that? Well, that gives you completely new semantics of intuitionistic logic. I call it the stable semantics. I stole this from stable domain theory. You replace worlds, which were opposite, by a distributive lattice. So you can now take intersections and unions of worlds. You can think of them as sets of information. Upper sets are now filters. What is a filter? In this particular case, it's something that contains a top world. And if it contains two worlds, it contains their intersection. Filters are a little bit like theories. They're closed under implication, conjunction, and disjunction implicitly. Okay, and here are some clauses. I've not seen these before. I've asked people. The best I've gotten is, it looks like a Beth clause. Please let me know if you know what it is. It's really extremely simple. Bottom can sometimes be true. It's true if your world is the top world. So the top world, one, is like a supernova of information. It even makes true false. I've written it this way for reasons I'll explain later. Disjunction is the same. Implication is exactly the same. Disjunction is different. It says if you can fan this W into two elements, these two elements together contain their common information is less than what you currently know, or possibly equal, then you should be able to validate phi in the first one and psi in the second one. Okay, so what if, for example, psi is false? You just put 1 there. So that's V1 and 1. So you're golden. So this works. This really works. And I've never seen it written down before. It's obviously sounding complete for intuitionistic logic. And there's a very similar story as before. So if you start from a distributive lattice and you take conjunction preserving maps, monotone maps, you get all sorts of interesting things. Like before, remember, it was upper sets, now it's filters. Before it was a complete hiding algebra, it's still a complete hiding algebra. The principal thing is a filter, actually, and now it preserves meets, joins, finite ones, and exponentials. So now, if I have a hiding algebra, that's a distributive lattice, I can embed it in the filters. So every model, every hiding algebra can be seen as an instance of this thing. Moreover, you've got this compactness thing from the main theory. So if you've got a directed thing, upper bound, and P is less than that, then it is compact. If there's something that is being upper bounded that is less than, and that's an if and only if it's a principal filter. Normally, if you read a Ramsky-Young or something, you'll see this as the ideal. But if you flip everything, you get filters. And every filter is a directed supremum of compact ones. Okay, this kind of thing is called a spectral locale. It plays a very, very deep role in stone duality, but I still don't completely understand. There's an algebraic, complete Hagen algebra, whose compact elements form a sublattice. I've got about 3 minutes.
9 minutes, including questions.
9 minutes?
Including questions.
Okay, that's a long time then.
4 minutes.
Okay, there we go. Okay, so very much the same as before. The main duality we're talking about now is one between distributive lattices and stable maps, stable being meat preserving. If you flip it around, you get these coherent frames from stone duality and Scott continuous meat preserving maps, so arbitrary meats, which is not the usual category from stone duality. It's a different one for some reason. And then you can, of course, prove that since one embeds into the other very nicely, they're both equi-complete. So if the algebraic semantics is complete, so is the stable semantics and vice versa. And you can show this constructively. I'm not going to go into the stuff on modalities, but it all works out fine if you read the Bramsky-Young for long enough. Okay, but if you go up to category, something very interesting happens. The first thing you need is you need to realize that you don't need a distributive category, you need a co-distributive one. So plus must distribute over product. I think that was today somewhere, right? Distributive Markov categories. Is anyone there? I saw this somewhere. Yeah, okay, I'm getting one nod from someone who knows what they're doing. So this is a thing. There's been one paper on this by Davey in '83. It's been cited 3 times. I thought that was interesting. Okay, so with 2-dimensional stable semantics is a semantics in a category of algebras. But the theory, the Lorvier theory, must have not just products, as Lorvier theories normally have, must also have co-products, and the latter must distribute over the former. I've never seen this condition before. It's really very strange. I don't know what it means, but it does mean one thing, and this is due to, I've attributed to Younes Kadar and Sam Staten between them, but I think it predates them. They still have not been able to answer this question. C is co-distributive if and only if the product preserving pre-sheaves from C into set is a Cartesian closed category. So that's a theorem. You can show it. It's a little bit of faff, but it's not too bad. And then you can embed every by CCC. If it's a by CCC, it is co-distributive. Yes, because this is co-distributive now, because every CCC is distributive. You can embed it into the product preserving pre-sheaves. For example, and this is a connection to MFPS. This is why it's not a logic paper. It's a programming semantics paper. The category of product preserving pre-sheaves over co-distributive C is complete for type lambda calculus with sums and an empty type. So this is the main theorem that you need to take away. But the interesting thing is, we started with filters. There's 2 ways to categorify filters. One is to take the end completion, the one that Gredendig did. That adds all filter colimits, but that's too much. By taking product preserving pre-sheaves, you actually have the sifted completion, which is what generates the algebras. So I spent a lot of quality time with Adamic, Vitale, and who's the second author? Book 2010, Adamic, Brzezinski, and Vitale. Yeah, so I spent a lot of quality time trying to understand that everything lines up. For example, these things, the compact things, they're really the absolutely presentable things. They are the very, very small algebras. If you go back to this, and you squint really hard at this, you'll notice the day convolution product, which is also the co-product of algebras. I had to prove that. That was not in the literature for some reason. It was in higher algebra according to Daniel Draper. If you squint at this, the idea that something is true, that bottom is true in the world, that happens when 1 is less than W. Okay, now think of this as a morphism. When do you have such a morphism in the Lorvier theory? When W is a sort, and you can make a closed term from the constants of the Lorvier theory, assuming nothing. So everything lines up perfectly and you get semantics in categories of alphabets. And I don't know what to do with this yet, but I think it's fascinating and it needs to be looked into. I think that's all I have to say. Thank you for listening. Thank you very much.
Yes.
In your tables, you only have the arrow going one way.
Yeah,
So my question is, do you have arrows going? I expect having little arrows going in all directions. These things.
thank you very much. I did not have time to do this before the MFPS deadline.
Part 3.
There's also 4 and 5 coming.
Sorry, I'm with you. Yeah.
So,
Sam?
See as the equal balance. So extensive, yeah. I think we can find we consider it as a Kavvos and use the extensive.
That would be nice. I got
Presumably it's the internal language. So my question was, if you'll see not really extensive.
is my C?
If you'll see or CR, not really extensive.
I don't know. I haven't thought about it. I got a very nice email from John Sterling about 2 hours ago, where he said that if your C is nice enough, it's a sheep Kavvos. I'm not sure I believe it, but I have to think about it. Again, not enough time before the MFPS deadline.
I'm not sure it's used in you.
Any more questions? I just wondered, what did you mean by complete for, it was the theorem that said some category was complete for,
Oh, the interpretation is complete. So this class of models,
yes.
if you interpret the lambda calculus in those models, and it's true in all of them, then the equation must be provable.
Uh-huh.
Because all CCCs can be found in there, in particular the free one, which is nice and small.
So complete as an equational theory with
Yeah.
two terms.
They're complete for proof equality,
Yeah. Okay.
not complete for provability.
Right.
But that should be fine too,
Yes.
by this.
Good. Any more?
in that theorem, I'm expecting, oh no, you're taking the pre, C, it's in the theorem, C doesn't have to be closed, right?
No.
Okay.
C, think of C as a Kripke frame. So C is like a proof relevant world thing where you can move around and you can add information and it's all proof relevant for some reason. Where this is going, I can't really tell you. My objective was to fill in the table. If I know that I can put an adjunction there, what does this become everywhere else? And so now we know that Fitch style natural deduction systems come from Kripke Semantics, which is not obvious before, I think.
Sam again.
So how would you answer my question? Should we ask C or C op to be extensive? How would you know whether, if I argue that you should, how would you argue that?
I wouldn't. I wouldn't. I would write another paper. It's 3, 4, 5, and 6.
That sounds like a good. That sounds like a good stopping point because we need a bit of time to change over. So thank you very much.